right. Yeah, not a huge crowd, but not too surprising given the flavor of this conference. So hopefully we'll grow the Python presence at NDC over the years. So this is the tip of the spear, I guess. So today, well, I'm Austin Bingham. I work for and half own with this fellow here, 60 North, a small software development and consulting and training company based out of Norway. And we do a lot of work with Python and have done so historically, not just with 60 North, but with other companies we've worked for. And today I wanted to give kind of an introduction to what I call the landscape of testing tools in Python. You may have seen some of these if you do any work with Python already, and hopefully you haven't seen them all, or I at least teach you some new tricks. We'll cover everything from, well, let's look at the agenda. I have modules for unittest, which is built into the standard library. I have a module on mock, on pytest, which is in some sense a replacement for unittest. And more exotically, a tool called hypothesis, which does property-based testing, and a tool called Cosmic Ray, which does mutation testing for Python. I'm the main author on Cosmic Ray, so if you have hard questions about that, I can help answer those. In the 60-minute format we have here today, we can't really cover all of this meaningfully, so I think we'll go with unittest, hypothesis, and Cosmic Ray in that order, and if we have time left, I'll do a quick intro to pytest. But given that we've really only got 4 people, is there a preference? Does anybody really want to hear about anything else in there? Okay, then we'll go with that order. And just real quick, are you using Python now? Okay, so it's not paying the bills. And how about you? You started Python last week. Your company did? Okay, well that's good. Then I think you really will get quite a bit out of this. We'll give you some good ideas about how you can effectively test your Python code, or at least start to do so. Right, so let's dig right in. This slide deck, by the way, is available on GitHub. I'll have a link later on. It's an IPython notebook. If you've never heard of that, it's essentially a way to mix text, notes, and actual code, and I'm hoping it's an effective way to present this material. So unit test. Unit test is testing with the standard library. It's built into the standard library, so that means that any Python installation that hasn't been mangled will have this, and that's perhaps its greatest strength, the fact that it's always there. The reason I think it's important to learn unit tests is because you will see it. If you start using any third-party libraries and any code that somebody else has written, you're very likely to run into it because it is sort of pervasive. And it's a powerful tool to know, and it's good to have. You can write spot tests very quickly with it, and it's a little bit weird. It doesn't follow PEP8 entirely. It does some strange things, but by and large, it's a very effective tool. The basic features that unit test and pytest and other tools in that area provide you are test automation. Obviously, that's its sort of raison d'etre. That's why it exists, to help you automate and have repeatable tests so that when you make a change, you can run your tests and go get some coffee and come back and see the results. It has facilities for doing setup and shutdown and tear down around your code, around your tests, what they call fixtures typically. So if you need to create temporary files or clear a database or something, it has tools for doing that. It allows you to aggregate and sort of organize your tests. So if you just want to run a subset of your tests, say the database stuff or the communication stuff or something like that, you can organize your tests in such a way that it's easy to select which ones you run. And it has a nice independence between the test execution engine and the test reporting engine. So if you want to make fancy reports of your own and inject them into some report that you present to somebody or put it up on a screen so everybody can see, it makes it pretty straightforward to do that. The basic way you organize tests in unit test is with something called test case. And this is a class, and you use it as a base class, you inherit from it, and then you can use some of its methods, and then you create your own methods that actually run the tests or implement the tests. So it provides basic assertion methods, by which we'll look at these in detail, but the assertion methods are how you express the truth you expect to hold at some point in time. We'll talk about fixtures, which are the way that you do setup and tear down for your tests, and some related test methods that we'll kind of see, various miscellaneous utility functions. The basic approach when you write tests in unit tests is you create a subclass of test case, and then you write some methods that start with the word test, and these methods get discovered by the unit test framework and then executed when you run things. So what does the simplest possible test case look like? It looks like this. And I should just point out this % unit test run. You'll see these things. Those are magic code words to the IPython engine to help it execute this. So you can ignore those. That's not actually Python code. I'm looking for a way to make those disappear in the slides, but it can't be done right now. But the basic structure is what you see here. This is a test case that does nothing. It inherits from test case and then just says pass. So it's doing absolutely nothing. But I can run this. So let's do that. Right. So what you expected, 0 tests run, 0 failures, 0 errors. So in some sense, that's really good. In another sense, that's just not terribly exciting. But that is that's the fundamental. That's the foundation of how you do things in unit test. The way you write actual tests that start to do assertions and make claims about how the universe ought to look, is that you create methods on your subclass that start with the word test. You can actually control that. You can configure unit test to look for different patterns, but by default it looks for methods that start with test. So in this case, let's try the laser here. We have our test case subclass, and we have a method here that's empty. And this will be detected because it starts with test. This also starts with test, although not test underscore. That's irrelevant, test or test underscore. This also gets detected as a test, but this does not, by default, get detected as a test. So this is invisible in some sense to unit test. So I can run this as well, and what we should expect to see is that 2 tests ran, no failures, no errors. Great. So still not the most exciting thing in the world, but you can kind of see now what unit test is detecting when it scans for tests. So now we want to look at assertions. We really want to start making claims about what we expect to be true when we reach a certain point in execution, or what we expect to be not true, or how we expect data structures to look and things like that. So there's a whole bunch of methods on the test case subclass called assert something. Assert that this is true, or assert that this is equal to this. And that's how you tell unit test to run tests. A failure of an assertion is a failure of a test. So how does that look? So finally, we have tests that do something. This test always passes because it trivially asserts true that true. Okay, so this is saying that whatever expression is passed in this case true, we expect it to be true. And if it's not, then if it's false, or false E in Python terms, then this will be a failed test. And this will always fail because we're asserting false. We expect this expression to be false, and it's actually true. So, of course, what we'll see is that we get 2 tests run, 1 failed, and test always fails is the one that failed. So this is my secret code, F for fail. And this, by the way, what you're seeing printed out here, I can do that because of the separation of the reporting engine from the execution engine. I was able to ask unit tests to run my tests, grab the results object, and then inspect it to figure out what to print down here. So this is an example of the separation of execution and reporting, which is not so easy to do in, for example, pytest, which is kind of why I harp on it a little bit. But this is finally an actual functioning test, and this is the flavor of what a lot of your tests are going to look like. A bunch of things that say test something, run some code, check some assertions, and that's it. And they'll typically be quite small. If they get to be big, you want to start looking at using fixtures, which we'll examine in a bit. There are a lot of assertions built into the test case class. We won't go over them all in detail. You can get these slides and see, but you can check that 2 things are equal or not equal, or true or false, or is not for reference checking. Is not instance if you need to check if something's of a certain type, and in, not in. There's a whole bunch of these, and you can see all of them in the test case documentation if you want to. But remember, these are all methods on the test case class. So if you look back here, oh wait, sorry, not there. That's why we say self assert false. This self, of course, is this class, instance of this class, and assert false is defined on test case. So that's the basic mechanism of how these assertions are made available to you. Another kind of thing you often want to check for, especially in Python, which is a very sort of exception-centric language. It uses exceptions for all sorts of stuff, and you're encouraged in your own code and your own APIs to use exceptions. You want to check that a certain kind of exception is thrown in a certain context. And so there's assert raises, also a method on the test case class, which you use as a context manager, so in a with block, if that's an exotic term for you. And let's see how that looks. So here we want to test that an index error is thrown in a certain situation. And so it's very synthetic. Of course, we say with self-assert raises index error. So we're saying In the context of this block down here, we expect an index error to be thrown. And of course, we just raise an index error just to simulate it happening, but you could imagine more complex code that did something that should raise an index error. Similarly here, we're going to have a failing test because we assert raises that a value error will be thrown somewhere in here, and of course, pass does not throw a value error. So we can see that in action. Great. So 2 tests were run, and test value error failed. So this is the canonical way, and the correct way, I'm going to say, to test for exceptions. You could, maybe in some really weird situations, need to use try catch and then assert inside the catch block or something like that to check for some bizarre situation. But by and large, testing for exceptions should be done using this approach. And this is identical to the approach used in pytest, for example. So it's an accepted idiomatic way to do this kind of work. And it's kind of elegant. I like this use of context managers here. It feels right. So fixtures, we've mentioned these a few times. Fixtures are essentially the way that you do test setup and cleanup. So before a test is run, I need to do some work to set the, to kind of clear the floor maybe, or create a temp file or something along those lines. And then after the test executes, I may need to clean up, remove a database table, or delete the file that I created, or any number of things. So there are essentially 6 hooks that you can use. There's test case setup. So this is a method, it's an instance method on test case. And setup, if you define it, well, it's always defined, but if you create your own, your code will be executed before every single test. And then teardown, similarly, is executed after every single test you run in that class. Setup class is a bit different. Setup class is executed once before any test in a class is run. And then teardown class is executed after all of the tests in the class is run. So only once. It's like a bigger sandwich than the setup and teardown. And then finally, setup module and teardown module work like this, but at the module scope. So setup module is executed once before any tests in a module are executed, and then teardown module analogously at the end. And we'll see, I'll try to demonstrate that here by showing you how, you'll see in a second. But so what are they used for? You can probably imagine a few things, but very common in my experience are things like creating and clearing database tables, putting a database into a known state so that your tests know what they're getting into when they start to execute, what you might call hygienic testing. Configuring instance members, so you can use setup and teardown to set values on the test case class itself and then use those values in the tests, or maybe create temporary files. This is very, very common in a lot of testing environments. But basically think of it as setup and cleanup. That's what fixtures are for. Excuse me. So how do they look in practice? So here we've created, yet another test case subclass. Setup class and teardown class are both class methods. If you're coming from C++, you would think of them as static methods or something like that. And these are the ones that are executed before any function before any test in a class, and this is executed after all of the tests in a class. And all we're going to do is print some strings so that we can kind of see the flow of the logic. I'm not going to actually try to do any real work in these. Similarly, setup and teardown executed before every test and after every test, and they're going to print something out as well so that we can identify the order of execution. I need to execute this cell real quick. All right. This next slide is a continuation of that class. So now I've added 2 test methods that don't do anything except themselves print. So what we're going to see when I execute this is the interleaving, the order of all these things that we're printing out. And hopefully that will make it very clear what's happening. So I run the tests. We get 2 total tests run, these guys here. The very first thing that happens, of course, is setup class executes. And then setup, remember, which is our function level fixture, executes. We run the first test, and then teardown executes. Setup runs again, test number 2 executes, and teardown happens. And finally, we do teardown class. So that's, in a nutshell, that's how these things interact. It's just various levels of scoping, effectively, for your fixtures. So you can imagine how this might apply to the test code or the code you're trying to test. Are there any questions about that? It's not entirely clear. That I feel like maybe that's a bit of a rough section, so yeah, as long as it's clear. One thing you can do in setup and very often need to do is configure member attributes. And this is a bit tricky for some people to initially grasp. They need to, when their conceptualization of the kind of the context of test execution is not clear yet. So I want to kind of drive this point home. You can use it to assign attributes on the class itself. And this makes perfect sense. This isn't rocket science, but it's a bit of a confusing concept sometimes. So in this setup here, we set self.data. So we're setting some data member on the class that's going to be self in all of these tests. We set it to some value. In both of these tests, we assert that self.data contains the value that's set in the setup, and then we change it. In both cases, we change it to something else. These don't step on each other because, of course, setup is executed before every test. So this gets reset essentially before every single test. And like I said, this isn't some mind-blowing news that's going to make you guys better human beings or anything. But it's good to remember that. I think if you get that, then you understand the basic flow of fixtures and how they interact with tests. So this is executed literally before every single test is run. Unittest main. This is, in some sense, it's a convenience function. What it does is scan the module in which it's executed for tests to run. So it looks for test cases and it looks for test methods, and then it executes them and prints a little report. So it's a really convenient little function. And what it's very often used for is to create little executable test modules. So if I've got my unittest main.py here, and it's created a test case that does some questionable tests, I can then go down here and, okay, I apologize, there's some kerning problems here, so I'm going to just go out of that mode. If you've never seen this before, dunder name equals dunder main, this is the idiomatic main function for a Python module. It's saying if this value, which is set by the Python runtime, is equal to main, that means that this module is being executed as the top-level module. And if so, do something special. Right, so this is kind of the main function. So all we're saying in a situation like this is, if I'm being executed as the top-level module, run unittest main, which means go find these tests and execute them. So it's really convenient to take your test classes and bundle them up into modules and have them executable in a standalone way. And so you'll see this pattern repeated over and over in a lot of unittest-based testing code. And I apologize again about the layout issue we had there. So if I then execute this, we'll see, actually I can make that look a bit better. So if I have unittest main py that we looked at just a second ago and I execute it on the command line, that's what this magic here is saying. It prints this report that the assertion failed because 1 does not equal 2, except in Bizarro world, and we get some stuff there. And that's all because we used that idiomatic dunder main equals dunder name block. So there's a few other niceties that I'm going to kind of go through quickly. If you need to skip tests, you can do that using certain decorators, and it's just an exception you can use as well. And it looks like this. If I need to skip a test for some reason, I can say, I can decorate it with skip and give a reason. And then you can execute your tests, and it will print out the reason things are skipped. And that can be really useful in cases where you have a test that doesn't work right now because something is broken that you intend to fix. And so you just want to kind of mark it as not working. You can skip conditionally. Maybe a test only works on AIX or something like that, and so you only run it on AIX. So you can check your platforms. If AIX is a strange term for you, you're lucky. And you can skip unless as well. They're just inverses of the same logic. So if we execute this, we should see, right, 3 tests run, 2 skipped, and some skips here. So you can analyze the test report to determine which things were skipped, which is really handy. There's also the skip test exception, which you can throw from setup or from your test functions. And what this will do is, if this is thrown and bubbles out of your test or your setup, unit test code will see that, recognize it, and say, okay, I'm going to count that as skipped. So if you try to make an uplink to a satellite and it's not available at that time, you should just skip the test. And the testing framework will say, okay, it's not really a failure, but I want you to know that we skipped it and why we skipped it. You could also throw this from inside your test, like I said, and you get the same effect. But these have the ultimately exact same effect as using the decorators that we looked at just a second ago. You can also, in this very similarly, you can say, I expect a certain test to fail. This is, I put a question out on Stack Overflow or Reddit and asked folks, like, what situations have you actually used this in? And this is another place where people said, well, I've got a test that is broken, I know it's broken, and I know why it's broken, and I expect to fix it, so I can mark it as expected to fail. And the reason this is useful is because the test runner will report to you that the test failed and I expected it to fail, but will also tell you I expected it to fail and it succeeded, meaning you somehow fixed the test. That's a really useful bit of information to get back. So if you're in some heavy development phase and things are in flux and you're marking things as broken and fixed and stuff, you get a nice report back in a test telling you what you fixed, maybe accidentally, and you might scratch your head and go, how did I fix that? I'm smarter than I thought. And it looks like this. We expect this test to fail, and if I run this, I can see, yeah. And if I somehow, fixed my logic and executed it again, it's going to go, uh-oh, I got an unexpected success. And that's really useful information. Somehow I've changed something that fixed the universe. Let's put that back. Right. That's cool. Running code in slides, it feels neat. So now it's become an expected failure again. Oh, because I misspelled false for one thing. Here we go. This is relatively new, parameterizing your tests. This showed up in 3.4, and what the discussions about this have been going on for years on the Python dev list. The basic idea is that you have a test that you want to, logically you want to run this test, say, 3 or 4 or 5 times with different sort of input parameters. The normal way to do that initially, a long time ago, would you'd have a list of these parameters and you loop over them. And if any one of them failed or caused an assertion to fail, the whole test would fail. And this was not great because it meant you didn't actually run all the tests you expected to run. And the reporting wasn't as fine-grained as you would like. So this notion of subtests allow you to mark a portion of a test using a with statement to say, this is a subtest. It's parameterized on a couple of different inputs. Run each of these independently. Treat them as separate tests. The failure of one will not mean that everything halts and the others fail as well. So, as with all these examples, it's a bit contrived. But, okay, we got a normal test case, and we're going to test that all the words in some list are ASCII. And obviously, they are not all ASCII. This is Norwegian for thread and Norwegian for island. So it's a bit of a da-da-da. Tråd and øy. But clearly not ASCII, right? So here we say, with subtest, binding word to this word here, it's a bit weird, but we're saying that in this context, we're binding the name word to whatever word is here, and we're just looping over this here, and we run a test. Fundamentally, what's happening is that this block here, this assertion, is going to happen for all 4 of these every time, and the failure of one assertion will not cause the others to not run and won't result in failure of all the other ones. So the output is a little bit what you might not expect. It says we ran one total test with 2 failures, and the failures were when the word was tråd and when the word was øy. So the other ones passed just fine. So if you find yourself, writing 5 or 6 tests that are basically the same test, just have some different parameter, think about using subtests. It'll clean things up, and it's much more expressive, and it gets your point across much better. I want to kind of close this section up with some advice, I guess, on how to structure things. I've personally gone through, iterations of how I think projects ought to be laid out, and I've had various reasons for believing that. But I've settled, and I think Rob is kind of on the same page with me, that this is a pretty good structure here. At the top level, you've got your project name, so foo. Underneath that, you would have another directory called foo, your project name that contains your dunder and its. This is actually your package in Python terminology. This is your code here. You'd have a setup.py, which I highly recommend. It's not required, but very, very useful. Critically, for the purposes of this discussion, you would have a separate test directory. That is, you would not have your tests inside your package. The main motivating reason for that, for me most of the time, is that I do a lot of mutation testing and mutation testing work, and I don't want these getting mutated while this code is getting mutated. That would throw things off in a really big way. Maybe more fundamentally, though, these aren't part of the package. They don't need to be part of the package, so putting them in the package is just confusing. It just conflates things that don't need to be conflated. So keeping your tests out here makes them a bit more independent from your package. It makes your package installable without the tests, for example. There's a number of reasons for doing this. This isn't required. Of course, you can use whatever setup you like, but you'll see this in the wild quite a bit, and it's a very effective, pragmatic way to structure your projects. And okay, so this is an example of a sort of a real test, just to kind of bring everything together. And I apologize because the underscores are invisible, but this is what a full test might look like. This is our test sorting that we looked at a second ago, just to kind of bring it full circle. With your import unit test, create the test case, have a test, do an assertion, and then have your idiomatic main down here to run unit test main. This is a complete thing. You could ship this, and everybody'd be happy. So hopefully that brings the unit test discussion sort of full circle for you, because that's the last slide, so it has to bring it full circle for you. Are there any questions about unit tests or anything that I've covered? Yes?
Is it only for Python 3 or is it also in?
Oh, unit test goes back to probably Python 1. I don't know how old it is, but it's been there forever. Yeah, do you know, Rob? It's ancient. Yeah. It predates, if you remember, we looked at the fixture function is called setup, right? And does everybody know what PEP8 is? PEP8, for those who don't know, well, a PEP is a Python enhancement proposal, and it's how Python makes changes. It's how we discuss changes to the language. PEP8 is a description of how code should be laid out, naming conventions and things like that. This is very not PEP8. This precedes PEP8, so it means it's really, really old. This naming convention using camel case rather than snake case would not be allowed, more or less, today. So it's quite old. So you can use it in Python 2 code very easily. Not all the features I talked about are in Python 2. Subtests, for example, are fairly new, very new. Most everything else, I think, is in there. And a lot of things have probably been backported if you need. It may be that subtests have been somehow magically backported to 2. I'm not sure. Okay. Well, like I said, because of the time constraints here, I'm going to skip unit test mock and pytest. I can just really quickly say, unit test mock is a way for you to test how an object is used. You essentially create these mock objects and then call functions on them, pretending that they were some other thing. And then the mock objects keep track of how they're called, and then you can inspect them and say, was the function foo called on you, and was it called 6 times? If so, then I'm going to say this test passed. It's a very sophisticated, kind of subtle library, but it's very useful in a lot of situations. Pytest is, you can think of it as a more sophisticated modern replacement for unit test. The basic difference between pytest and unit test, if I had to summarize it, is that pytest is lower ceremony. To create a test function, you don't need a test class or anything. You just have def test underscore something, and that's your test. And instead of having these assertion functions like assert false, assert true, you just use the standard assertion keyword. And then pytest is really clever about catching assertion errors. Because point of interest to Python people, what happens when an assertion, when you say assert, A-S-S-E-R-T space some expression, Python on failure throws an exception, which you can then catch and deal with, and that's what pytest does. So it's not like in C where assert causes you to just, segfault immediately. So if we have time, I'll get back into pytest, but I want to show you hypothesis because this is one of my favorite tools, most favorite tools in the past few years, written by a friend of ours called David McKeever. Very, very, very smart guy. So hypothesis is property-based testing for Python. And if you want to go read more about it, you can go to hypothesis.works. That's the URL. Property-based testing in a nutshell. Well, we'll get to that. I like David's quote, though. The larger purpose of hypothesis is to drag the world kicking and screaming into a new and terrifying age of high-quality software. So if that's where you want to be, and he's a bit hyperbolic, that's how he is, but he's smart enough to get away with it. So the Hypothesis Manifesto is worth a read. The basic idea of hypothesis testing is that you define invariants, or you state hypotheses about how your code ought to be, how the state of the universe ought not to change or should change, no matter what, given that your code works properly. So you make these statements using assertions. You then tell hypothesis how the test can be ran and what parameters your tests need to be fully tested. So you define these invariants and say that no matter what values you give me for these parameters, this test will always pass. And the hypothesis does the really hard job of searching systematically and very methodically for parameters that cause your tests to fail, right? And that's its key power, is that it's really smart about searching potentially infinite spaces for parameters that can cause your tests to fail. And then when it finds a failure, it has really clever logic to reduce those input parameters down to the simplest possible versions. So if it finds some input list that causes your assertions to fail, it will work to shrink that list down to a minimal example. It's really, really clever. And I find I have trouble expressing how much it's changed the way I approach testing in Python. It's a mental shift. Oh, did you have a question? Oh, sorry, I saw a hand up. And there's a bright light right in my face. So any motion is like, oh, what's going on? So hopefully I can get across to you at least the idea of it, if not my pure unbridled enthusiasm for the project. So, okay, we need a motivating function, something we want to test. So this is an implementation of greatest common divisor. It's not the best implementation in the world, but I can fit it on a single slide. So you may or may not believe that it works, but I'm pretty sure that it works. So it just, taking m and n, returns for you the greatest common divisor, the biggest number that divides into each of them with a 0 remainder. Oh, I need to execute that so it's in the scope, in the session. So how would I normally test this? Without hypothesis, I would probably do something like this. I would say, well, one thing I know is true is that whatever d is, whatever the divisor is, it needs to divide evenly into m and n. So I just check, does m mod d give me 0, and does n mod d give me 0? And I would test that for some set of input numbers, right? In this case, I'm saying, for m from 1 to 1,000 and n 1 to 100, give me the product of those and pass them into this function here, bind them to m and n and run them. So I'm doing some work of guessing what I think a reasonable input range is. And similarly, I'm going to test that whatever d I get back from GCD is actually the biggest number that fills the bill. So this test is basically saying there's nothing bigger than d, which evenly divides into m and n. So these in a sense are my assertions about what should always be true. And then this is me doing some heavy lifting to figure out the inputs to pass to my functions. And we execute those cranks for a bit because these are actually reasonably big state spaces. And then we see, okay, 2 tests pass. So it looks like our GCD is in pretty good shape. What hypothesis is going to do is this work for us. It's going to do it smarter and better than us. It's the bionic man of input parameter calculation. So this looks a bit more verbose because it is more verbose, but it's actually doing a lot more. This is the hypothesis version of what's going on. And so let me kind of step you through the parts. And I apologize, I secretly imported given earlier. Given is from hypothesis, and it's the decorator you use to explain to hypothesis how to bind input values to your test function. We have these things called strategies that we'll look at in some detail, but strategies basically are the things that generate input to your test function. So, putting it all into English, what's happening here is we're saying given that I have one strategy that produces integers between 1 and 2,000, and another strategy that generates numbers between 1 and 2,000, bind those to m and n and execute my test function. Try to find values for m and n that cause a failure in here. I should also point out that I put a limit on these purely so that I could run the tests here. If I didn't put limits on those, hypothesis would feel free to run for not unbounded amount of time, but for longer than I had patience for. So you can see it ran pretty quickly. But that's the fundamental idea of hypothesis. You give a simple explanation, hopefully relatively simple explanation of what you expect to always be true. You tell hypothesis how to kind of punch your function, and it will do that until it finds a failure or it gives up. So of course it can't search all integers because in Python all integers is infinite, right? So we'd have infinity times infinity, which is mega infinity. We can't search that much space. This is doing effectively the same thing. So we'll look in detail then what are the smaller moving parts inside hypothesis. But this in a nutshell is what a hypothesis-based test looks like. You have very, very much smaller test functions in general, and your test functions are less baroque. They're less complicated. They're kind of plainer statements of truth. Right? How are we doing on time here? Good. So I mentioned strategies, and these are the things that you use to generate input into your functions. This is where the real cleverness of hypothesis comes in. That it does these things in it does them quickly. It does them in statistically valid ways, so you get nice distributions across whatever range it is that you're trying to fill up. And it can do it for simple things like integers and text, but also more complex things like fractions or lists, complex data structures, lists of Booleans in this case. So what we're going to see here is, when I run this, a list of one example from each of these, just to kind of prove the point that it can be done. So we see we got an integer 190, we got some random text, we got a fraction, and we got a list true. So this is great. With very little effort, we were able to convince hypothesis to give us some test values. And that's the kind of data that just plugs into your test. There are primitive strategies for pretty much everything you can think of. Floats, integers, booleans, more complex things like text and binary, and vastly more complex things like UUIDs and fractions. And you can write your own strategies if you want. But very often you can get by just using these. This is a sort of full-fledged example. We're going to show that, given a UUID, a fraction, and a binary of some certain size, run this test. And really the point here is just to print out what hypothesis generates. So all we do is print out the things that come in and basically assert false. And let's look at what's getting printed out here. It runs once, and then it runs again. So hypothesis is doing some scanning in that sense. It said, okay, I passed you some input, and you failed. It could be that you have a kind of non-item potent test function. So I'm going to try it again with the same input. And oh, look, it failed again. So now I'm going to say that everything is dead, and I've come up with the falsification of your hypothesis, and here's what did the work. So one failure, and that's what failed. Okay, not terribly exciting to look at this output, but to give you some sense of what hypothesis is sort of doing in the background. It's very sophisticated about the kind of work that it does. There are more complex strategies for constructing lists, dictionaries, streams, tuples, all the kinds of things you would need to construct in a Python world, containing elements drawn from other strategies. So you kind of compose strategies, and we can see that here. We want to create dictionaries of integers to text, map keys of integers and text values, and we want to create tuples of floats. And if we just run this, we'll see some examples that it generates. And you'll see that it starts off with some very, very simple examples. What's the simplest possible dictionary of integers to text? It's the empty dictionary. What's the simplest possible tuple of floats? It's this, one tuple. You could argue that actually an empty tuple would be even simpler, but it wouldn't have any floats in it, so it'd be hard to argue that that's a tuple of floats. Static typing and dynamic typing, there you go. But again, nothing earth-shaking here, except that we can kind of see what hypothesis is doing in the background, what is passing into us. Kind of quickly go through the rest of this so we can get on to Cosmic Ray and hopefully some pytest. Every strategy has a function called map, and it also has a function called filter. So map takes the output, whatever examples generated by the strategy, and runs a function on it, and then whatever comes out of that function is what's pumped into your function, into your test function. Filter similarly takes the output of a strategy, runs a predicate on it, and if it's true, then passes it down into your function. Otherwise, it filters it out. So here we use an integer strategy, and we map this function over it. So instead of just integers, this is going to produce only even integers, because it's going to take whatever comes out of here, x, multiply by 2, and that becomes the value that gets pumped into x. Similarly, we're doing exactly the same thing here, except we're saying anything that comes out that's not evenly divisible by 2, that is, odd numbers, are filtered out. So only even numbers come out of here as well. So map and filter. I mean, if you ever use map and filter in any other language, if you've used link or anything like that, these are very familiar, hopefully, to you. These are not difficult concepts, but they can be a nice way to generate specific streams of data, so to speak. Flat map is a bit more sophisticated. A bit harder to explain, but in this case, and this is drawn, I think, directly from the hypothesis documentation. We have a strategy here, and we say just generate integers between 1 and 2, really. I guess I think this max value is 1 more than what you get. That's my experience, at least. Pass that value into this lambda here, whatever function is inside, pass to flat map, and then use the result of that as the actual strategy. So it's a way to bind the output of one strategy and use it to parameterize another strategy. So what this overall strategy is going to give us is a list of lists of integers, and these lists inside here are going to be of a specific size, a fixed size, n. So whatever number comes out of here gets bound to n and works there. That's a bit convoluted if you've never dealt with anything like flat map. So come back to it later. You want to spend more time on it, but it's good to know about. This can help you construct some very sophisticated data structures if you need to. We can run this just for fun. Right, so we see if we run it, we get 3 lists all of size 1. If I execute it again, I should get, well, okay, that's valid, as is that. These are lists of size 3, and on, and on, and on. These are all coming from the same strategy right here. I guess we never talked about this, but you've seen it several times. If you have a strategy and you call example on it, it gives you an example of that strategy. It takes one element from that strategy, so you can kind of probe your strategies. Interestingly, I was talking with David about hypothesis and what I should stress in this presentation. He said that he's finding more and more he uses strategies completely outside of the testing context. They're a great way to generate data for all sorts of purposes. He does a lot of what I would classify as research into voting algorithms and things, for example, and he uses his strategies to generate input into his voting simulations. It's not testing, it's not hypothesis testing or anything like that, it's something totally else, but it's a useful way to apply these very powerful tools. Other goodies, you can use this thing called recursive to generate things, for example, like JSON data structures, YAML, or any big complex recursive thing. You have a thing called composite for combining strategies in arbitrary ways, and data for interactively kind of getting information out of strategies. So all these things, we're not going to talk about in detail, but you can look at them on the Hypothesis website. We've seen this a lot already, the given decorator. Given, we say @given, and then we describe the parameters we want pumped into our test. It's just the way of binding strategies to input values. So we won't go over these in detail, but you can use keywords if you want to define the mapping between strategies and arguments. By default, it's all positional. And yeah, it kind of all works very intuitively and works well with the testing tools that Hypothesis is embedded inside of. For example, if you think about how these might interact with, well, we haven't looked at pytest yet, so it's a failure on my part, but pytest also wants to pass parameters into your functions, and so how does pytest play with Hypothesis? If you start running into situations where that matters, you need to read the documentation for both very carefully to understand which of these are being dealt with by Hypothesis and which are being dealt with by, for instance, pytest. But you can see here, I say given that x is integers and y is floats, then obviously, the mapping is pretty straightforward. In this case, we're using purely positional information to describe how to map this integers to x and this floats to y. And here we're saying, well, that x is integers, and it goes down there, and floats is going over here. And so you can kind of see there's an interplay of different orderings and ways of binding your strategies to input parameters. That's a bit of a ramble, and I apologize for that, but it all is actually very simple in practice, but there are some subtleties to how it all works. And so sit down again on your own and kind of think about what needs to happen. We'll skip over example because it's not terribly critical, but the basic idea is if I've come up with some input parameters that I know I need to test, that I know are critical, I can use example to say, always guarantee that you're going to pass these as input, and always guarantee you're going to pass these as input. Generate some of your own, but always use these. So if I found somebody give me a crash report and said it always crashes when I pass in foo, well, I want to make sure that foo is one of my input parameters, and you can use the example decorator to do that. Assume is an interesting one. Assume lets you tell Hypothesis that I know something's about to fail, but don't count it as a failure because I want you to assume that that value is never passed in. So it's a word trick almost, and it makes much more sense if I show you an example. So I want to test that a floating point number negated and negated again is equal to itself, right? That should hold for floating point numbers, except for nan, right? Nan, it doesn't follow these rules because it's not a number. Wonderful. So we use assume here to tell Hypothesis, look, we know that nan might come into this function. You might generate it because it's a float. It's a totally legitimate thing to pass in as x. In fact, I'd be surprised if it wasn't passing in nan. We want you to assume that x is not nan. And what this is telling Hypothesis is that, okay, this is going to fail. We know that. But since we've told you to assume that x is not nan, when this fails and x is nan, just don't count it as a failure. It's that simple. It's really... I call it a linguistic trick because you have to kind of read it as English for it to make sense. But you're telling it, just assume that x is not nan. Secretly, we know it could be nan, but we're going to say that if it is nan and we fail, it's no big deal. And if I run this, well, I mean, it's just going to tell me everything worked fine. If I take this out, I imagine actually, yeah, it will fail because x was nan, and that doesn't work. This logic fails. So let's put that assume back in, so that we can ship this. Right. There's a thing called stateful testing that is kind of new. It's new and semi-public, although David assures me that it's generally ready for use. The idea is that you can work at a higher level than just single test functions. You can define your API and the interaction of your API functions with the state machine. Pass that state machine into Hypothesis and point it at your test, pass it some strategies to parameterize the execution of your API, and it will try to run your API in the legal ways defined by that state machine and find failure modes, look for assertions that trigger. I've never used it. it sounds really cool. I'd love a chance to. I just haven't had a reason to yet. But David assures me that it's super cool, and I trust him. Further topics, there's all sorts of stuff you can read about. There's special support, for instance, for Django, NumPy, and things like that if you are using those technologies. I really want to end this section, though, by saying that I highly encourage you to check out Hypothesis. Even if you have a test system you already like and are happy with, it is really powerful, and it's helped us, for example, to find really obscure, weird bugs that we never would have found on our own, just by the dint of the fact that it's very, very smart. It's smarter than us at deciding what's a good input parameter. So on that note, try it out. It's very, very cool. We have about 15 minutes left. That's plenty of time for Cosmic Ray and maybe a bit of PyTest. So Cosmic Ray is the cutesy name for a tool that we've written for doing mutation testing in Python. If you want to get it, it's all open source on GitHub. And I'll talk a bit about what mutation testing is and then some specifics about the tool itself so that you're not totally ungrounded. Does anybody know what mutation testing is? Okay, good. And this will be mildly educational. I have a full talk on that as well. If you want to talk about it afterwards, I'm happy to talk your ear off about it. So what is mutation testing? This is taken from pytest.org. Pytest is a Java mutation testing tool, and it's the gold standard. It's really, really good at what it does, but it doesn't work for Python code, so we had to write our own. It's conceptually quite simple. You have your tests, you inject, automatically seed faults into your code, and then you run your test suite. If your test suite fails, that's good. It means your test suite detected that change. But if your test suite passes, it means that the mutant survived, and that's what you don't want. And you can use mutation testing to gauge the quality of your tests. That's really what mutation testing is about. Not testing your code per se, but verifying that your tests are actually doing their job, that your tests are high fidelity enough to determine when you've broken things. So what happens in mutation testing? We have our code under test, so your package, your library, your application, and you have your test suite. They really need to be separate here, which is one of the reasons I advocated earlier, keeping your tests separate from your production code, so to speak. It makes this kind of testing simpler. You then introduce a single change, a very small change, and we'll look at some examples of those. And you run your test suite, and hopefully all your tests something in your test suite fails. That's the ideal. That means that your test suite detected the change, killed the mutant, and you have a good test suite. The basic algorithm is something like this, without going into too much detail. There's some list of mutation operators, and mutation operators are the knowledge about how to make a small change to your code. You replace an operator or replace a constant or something like that. So we have some list of operators. For any particular operator, there's n places in your code that it might be able to change, right? There might be n many, greater thans that it could turn into less thans. It mutates that site, and then it runs your tests. So I call this a triply nested loop for operators, sites, and tests. There are m many tests you want to run. So anybody with any experience in software knows this is probably going to take a long time. If I have a million lines of code that are all getting mutated and having my test suite run, that can add up to a large amount of time. And that is one of the Achilles heels of mutation testing, that it takes a long time. And a lot of the effort and research in it right now is aimed at making these things faster. What does mutation testing tell us? Well, it'll tell us if it killed the mutant, that is, if the test suite failed. There's also a class of mutants called incompetent mutants, which are ones that can't run for some reason. Maybe they immediately throw an exception or segfault, or they don't compile, or something along those lines. It's the class of mutants that you can't test, so you can't really say that you killed them, but they don't pass. They don't pass your test suite either, so you just flag them as incompetent and count them as killed. And then there's those which survive, for which your test suite passes. And these are the ones that should raise a flag for you to force you to look at your code and decide what's actually going on. What are the goals? Why would you go through all this trouble? Because it's quite a bit of machinery and work. One is coverage analysis. Some of you, or actually all of you, have probably dealt with the traditional notion of coverage analysis, where you say, when I run my test suite, do 100% of the lines in my production code get executed? Are they passed through the processor at some point? That doesn't really tell you all that much, because it doesn't tell you if your test suite is actually verifying the functionality. So the goal of mutation testing is to tell you, is your test suite actually testing functionality and not just exercising lines of code? There's a big, big difference. And there's not time to really cover that, but intuitively, they are fundamentally different things. And this is what most people get with coverage analysis, and this is the goal of mutation testing, actually verifying that your functionality is being tested, properly tested. The other is to detect unnecessary code. So one of two things might be the case if a mutant survives. It might be that your tests are not sufficient to detect and fully test your functionality. The other is that you've got a bit of code in your package that you don't need anymore because it actually doesn't provide any functionality. So it's not that you're missing a test, it's that you've got too much code, and you can delete that code. So when you get a survivor, it's up to you, the engineer, to sit down and think about which of these cases holds. Or both, could be. So Cosmic Ray is the tool we've written to do this kind of testing in Python. At the center of Cosmic Ray is this notion of mutation operators. What do? They first can identify potential mutation sites. So they're passed an abstract syntax tree, and they report, yes, this node I know how to mutate, and this node I know how to mutate. And then the machinery of Cosmic Ray sort of iterates through the AST and at the right time says, okay, you found this spot, now I want you to make your mutation and hand the AST back to me. So AST, abstract syntax tree, for those who aren't up on the terms of art, but it's a data structure representing your code fundamentally. And then Python can take an AST and compile it into code that can then be executed. It can replace the module at runtime. So these operators really are at the core of what mutation testing is doing. Examples of mutation operators, we talked about this one, replacing relational operators. So maybe I find a greater than, I want to make it into a less than or equal or something like that. These ought to be testable things. If I make such a gross change to my code, it ought to be conceivable that I have a test that detects it. It's not always the case, and there are some fairly pathological examples where you actually can't test for certain changes, and that's another research area in mutation testing. Another example, constant replacements. Maybe I replace a 0, literal 0 with a literal 6. And if that's an index into a list, that really ought to cause a detectable change in my behavior. More sophisticated things include exception swallowing. It might say, oh, that's a nice catch clause you've got there. What if I just caught all the exceptions and never let them bubble out? That should cause behavioral changes you can detect. So these are the flavor of what mutation operators do. And there's a whole list that I would like to eventually implement, but we've only got a handful of them so far. There's a notion of sessions, and a session essentially wraps around the notion of what's a database, fundamentally, of all the mutations and all the tests you want to run, and then as the results arrive, the results for those test runs. And so in a Cosmic Ray run, you will initialize this database, and you scan the code to figure out what work needs to be done. Then you'll execute that session, and it will start, as results arrive, it will put them in the database. And this is nice because it means you can kill a session halfway through, and results that are in there, and results that are not, you can then pick up and get later by re-executing the test. So it's a nice way of keeping results around then for reporting as well. So this notion of session is sort of central to how Cosmic Ray executes. We have 2 execution modes currently. It's a pluggable architecture, so you could have more. I'm not sure what they would be, but one is you can run everything locally, just on your local machine. The other, which will be suitable for real-world use, I think, is using Celery to distribute tests through a task queue to other machines, or to your local machine, but to as many machines as you want. Celery is a very powerful task queue, and it's been a real win for this project. The mutation mechanism, just because it's interesting, I like to talk about this. We use the AST module so we parse code into an AST, we manipulate the AST, and then we compile it into what's called a code object. Python has this technology called finders and loaders, which are used when you say import something. Finders and loaders are the machinery behind the scenes that figure out what to inject into your current namespace. And we kind of hijack this to inject mutated code into the proper namespace. We use one Python process per mutation as a sandbox technique, because without that, you have the potential of the mutant actually breaking the runtime and breaking the test execution framework, and that would be really bad and really hard to detect. This is really important to me aesthetically and because I feel that it's a good goal for the project, that you can use Cosmic Ray without having to modify your tests or your production code. This is an ideal. We haven't been forced to deviate from this yet, although we do need to think about how to handle certain kinds of exceptions, and that may require that we inject special comments into the code. But we're not going to force you, though, to make radical changes to your code to run Cosmic Ray. So what's a full example look like? Well, I can show you the code here, but actually let's just run it. So here I've got this is a Celery task queue. There's a worker sitting at the end of this task queue that's going to take work to do. So the very first thing we need to do is initialize. I can make that a bit bigger. That's a bit too big. Okay. Is initialize a session. So we say Cosmic Ray initialize. Baselining is it's how we tell Cosmic Ray how long to run before it considers something to be in an infinite loop. We tell it we're using pytest. The session name is NDC. The test module is called Atom, and this is arguments to the pytest runner. So all this is going to do when I push return is scan Atom, figure out all the mutations it needs to make, and make a little database for us. So there's this ndc.json is that database. Now we want to execute in distributed mode the session we just created. So I press return here. If I come over to my Celery worker, we should eventually see it start to spit out information about work that it's doing. There we go. You'll also notice that all 4 of my processors are pegged now, and that's because Celery is really smart about knowing how many processes it can run reasonably on my machine. In that case, that's 4, because I have 4 cores, I assume. So it's running 4 parallel Python processes, each doing a single mutation and then fully running the tests. And now my processors are back to 0, so we come here and see the execution is ended. And finally, the drum roll, the report says, great, there were 56 total mutations we made. We've run all of them, and the survival rate was 0. That's solid. That means that our test suite was high fidelity. Now, okay, this test suite and code is all taken from the Cosmic Ray test suite, so of course it's really, really good. I'm going to go in, and really good in the sense that it catches all the mutants. What I'm going to do here is, this is one of the tests that we just ran. I'm going to comment that out. Conceptually, well, what's going to happen now is without this test, there's some mutation that's going to happen in the code that no longer has a test designed to detect it. So what we're going to have now is a mutant that survives. And I know it sounds really scary, but don't worry, it's okay. So we reinitialize the session. We re-exec the session. We let it run for a few seconds here. If we really want to go and watch the fireworks, it's all over there. It's kind of comforting to watch this. I feel that I can see progress being made because my tests are being executed. And then it runs and runs and runs. It's almost done. Right. Now when I do a report, I ought to see that I had at least 1 survivor. And indeed, at the bottom here, the survival rate was 3.57%. 3.57% of the mutants we created. I don't know if I would trust that precision, but that's the number we've got. More interestingly is that it gives us a little diff, a little patch here to show us what it changed that didn't trigger a failure. And here we can see what happened. We started off with this line, return object and none. We changed it to return object or none. That's a pretty substantial change, and so this is some logic that we had a test for, but without that test, Cosmic Ray said, I'm sorry, that mutant survived, you're fired. So that, in a very small nutshell, is Cosmic Ray and mutation testing. We really don't have time to go into pytest, but what I will do is give you some links. If you want this full presentation, you can just go to this address here, or just talk to me. I'll point you in the right direction. It's got instructions on how to set it up and how to run the slides if you want to do that. If you want to learn more about Python, we've got a book you can get. We've got a special discount code for everybody. It's like $7, I think. We do training and consulting on this kind of stuff if you're interested in that. And on that note, let's see if this works. Right. Any questions? So we've got a few minutes. Yeah.
Are you familiar with fluent assertions, like in C#?
I'm going to say no. I've heard the term, but it doesn't.
Yeah, I mean, it makes the syntax of testing a bit more human readable. Instead of using assert, you say the variable x should be false.
Oh, like the kind of stuff you see in some of these Java test frameworks like Jasmine and stuff. Yeah, I've seen those. I didn't know that was called Fluent, though. Okay. Probably.
Yeah, there's a port of, is it Hamcrest, which is used in Java? Yeah, there's a port of that.
Yeah. I would imagine that's a drop-in kind of thing. You can just drop that into any testing framework. It's sort of orthogonal to the... Okay, well, I guess that's about it. I love to talk about this stuff, so if you want to, just grab me at any point in the conference, and I'll be happy to chat with you about it. And hopefully next year there'll be more Python stuff at this conference. So talk to the organizers. Tell them you want more Python. It's good for everybody. Thanks.